Hello YouTube. So in the last video we examined the deductive-nomological model, which holds that to give an explanation is to deductively derive the explanandum from some set of initial conditions plus relevant natural laws. And this is quite a nice simple model of explanation, but the trouble is that it quite clearly doesn't account for all scientific explanations. So let's say that Julie develops breast cancer at 50 and we want to know why she got it. Well, because she had a harmful BRCA mutation. The BRCA genes are important tumour suppressor genes, and mutations in these genes, which damage their function, will substantially raise a woman's risk of developing breast cancer. And of course, if we want a further explanation about how those genes arose, well, we could tell some sort of story about how the damaging mutation arose and how it spread and so on. But the point is, this seems like a perfectly adequate explanation of why Julie developed breast cancer. Pretty clearly, though, it doesn't involve appealing to a law of nature, nor does it involve any kind of deductive inference. It's not a law of nature that all women with the BRCA mutation will develop breast cancer, so we can't deductively derive that Julie will develop breast cancer, given that she has this mutation. Instead, it's probabilistic. The BRCA mutation substantially raises the probability of developing breast cancer. Many scientific explanations seem to be probabilistic in this sense, and especially when we consider the sciences beyond physics and chemistry, in biology, if there are any laws at all, they seem to be probabilistic laws. Take Mendel's laws, like the law of segregation. So let's say we have a man with brown eyes, and he has one allele for brown and one allele for blue. Obviously, the brown allele is dominant, so the man has brown eyes. What are the chances that his offspring will get the dominant brown allele from him? Well, the law of segregation says 50%. 50% of the man's sperm carry the brown allele, 50% carry the blue allele. So it's a coin toss which one you're going to end up with. And this is true in general, but there are all kinds of exceptions. So there's a phenomenon known as meiotic drive, where a gene can manipulate the process of meiosis so as to cause itself to be transmitted more than 50% of the time. We find these kinds of exceptions cropping up all the time in biology. Pretty much every biological law that anyone's ever come up with seems to have these exceptions. And so you wouldn't be able to make the kind of deductive inference that Hempel says is required in a scientific explanation. Now, to deal with this, Hempel develops a slightly different model, known as the inductive-statistical model. And this works essentially the same way as the deductive-nomological model, but it appeals to probabilistic laws, statistical regularities rather than universal regularities. And this gives us an inductive rather than deductive argument for the explanandum. Let's take the Julie case. Here's basically what the argument will look like. We have the initial conditions in premises 2 and 3, stating Julie is a woman. Julie has the BRCA mutation. And we might want a few more initial conditions here. We'd probably need to add that she doesn't have any other genes fulfilling the same function, and so on. The statistical law is that most women with the BRCA mutation are likely to develop breast cancer at a young age, and so we get probably Julie will develop breast cancer. So this has the same general form as the deductive nomological model, but it appeals to a probabilistic law, and obviously it's an inductive argument. We can only say that Julie will probably develop breast cancer. But in many ways, it basically works the same way. So you can notice that this explanation shows us that Julie's breast cancer was to be expected, at least to a certain degree of probability. So this can also function as a prediction. If we had examined Julie when she was 20, we would be able to say that she's likely to develop breast cancer in the future. We would predict that she's going to develop breast cancer in the future. And I'm sure you can see how this can be applied to Mendel's laws and various other cases. According to Hempel, the deductive-nomological model is an ideal. Some scientific explanations are given in terms of the deductive-nomological model, but many explanations are not. But they can still be good approximations of the deductive-nomological model. So we don't need a universal law, as long as there's something analogous to a universal law. You know, as long as we've got a probabilistic law, that will do. All good scientific explanations are going to have the same general structure as the deductive-nomological model. Now, I should note that this kind of concession to inductivism raises various problems. Most notably, we saw in the last video that there are difficulties with the notion of a law of nature. It's very difficult to specify what distinguishes a universal regularity from. So it's very difficult to distinguish law-like universal regularities from accidental universal regularities. And it seems like if we're going to start appealing to probabilistic laws, then it's going to become even more difficult to specify what counts as a law of nature. So that would be one problem with this kind of approach. Okay, let's turn to some further objections to Hempel's model. So first of all, it seems that not all explanation appeals to laws, not even probabilistic laws. A good example is that one of the symptoms of syphilis is paresis. And this is a kind of muscular weakness which causes partial paralysis. So if John has paresis, we can explain why he has this by showing that he has untreated syphilis. The problem is that paresis is a very uncommon symptom of syphilis. Only a small percentage of people with untreated syphilis will develop paresis. So it looks like there isn't even a probabilistic law here. And this kind of problem arises with many other cases as well. You find it a lot in medicine. Stevens-Johnson syndrome is an extremely serious disease that causes skin to peel off. And it can be caused by various medications, so some thrush medication like fluconazole, but it happens only very rarely. It's a very uncommon side effect. So there's not even a probabilistic law that links taking the medication to developing Stevens-Johnson syndrome. This is something we find in general in biology and history and psychology. The fact is these fields just don't seem to be structured around laws in the way that physics and chemistry are. If we're doing history, we might try to explain why the Holocaust happened, and we can appeal to things like the history of anti-Semitism in various countries, then the production of anti-Semitic propaganda by the Nazis. We might focus on Hitler's rhetorical techniques, how Hitler managed to persuade the German population, and so on. But in none of these cases does there seem to be there's not there won't be a probabilistic law linking, for instance, Hitler's rhetorical techniques and anti-Semitic propaganda to the Holocaust or to genocide events. So this problem is closely related to another difficulty. We've seen that Hempel defends a symmetry thesis. He says that explanation and prediction are logically equivalent. It just depends on when the argument is given. The trouble is, it looks like some explanations just can't be turned into predictions. If somebody has syphilis, you wouldn't predict that they will develop paresis. You'd actually make just the opposite prediction, because it's more likely that they won't develop paresis. But still, we think the syphilis explains the paresis. So these criticisms have been seen as quite substantial, but I think there's a fairly obvious response to both of them. The response is, well, actually, there are laws involved in all these cases. It's just that we don't know the laws, or perhaps that we would need to specify the initial conditions in far more detail than is practically possible. So it seems to me that there surely is some sort of regularity with respect to syphilis and paresis. So with the people who develop paresis, there is some biological difference in their bodies that makes them more susceptible to it when they have syphilis. When we explain the paresis by appealing to syphilis, we've only given a partial explanation. There will also be other biological facts about them that make them different from most other people, and that's why the syphilis leads to the paresis. And it's the same with Stevens-Johnson syndrome. Something about your body is different, so the medication interacts with it improperly and causes that syndrome. And notice that scientists do in fact spend their time trying to uncover regularities like this. We study Stevens-Johnson syndrome more closely so that we might discover certain classes of people who are more disposed to it in virtue of the biological facts about them. This kind of scientific work has revealed a lot of information about the individual differences in biochemistry and hormones and immune responses and so on. I mean, it does seem like if we don't appeal to at least probabilistic regularities, it's not clear how we can distinguish explanations from mere sequences of events. When we give an explanation of y, that's going to involve telling some sort of story of x followed by y. And the idea is x explains y. But without some regularity linking x and y, how does that explain anything? That's just, you've got one event and then you've got another event. So it does seem as though there's going to need to be some sort of regularity, some sort of link. Hempel introduces the idea of an explanation sketch. And the thought is scientists very frequently won't give complete explanations, but instead pointers in the direction of where the complete explanation lies. So we have, why did Frank develop Stevens-Johnson syndrome? Because he took fluconazole. So that we have an argument like this. People who take fluconazole and who have further conditions K will develop Stevens-Johnson syndrome, and this is the law. Premise 2, Frank took fluconazole and had further conditions K, so Frank developed Stevens-Johnson syndrome. These further conditions K, that specifies where later scientific research should focus. Obviously, this isn't a complete explanation, but it's kind of good enough because that sort of expresses what we know and points us in the direction of where to do further research. And of course, this also answers the symmetry problem. Once we understand these further conditions K, we can use them to make reliable predictions. And this seems fairly intuitive. If we knew enough about human biology and we had a good understanding of every individual body, we would be able to predict when fluconazole would cause Stevens-Johnson syndrome. So it's still the case that all good explanations can be turned into predictions. However, there is another objection to the symmetry thesis, which is that not all predictions can be explanations. This is because we can make good predictions using false theories. Ptolemaic astronomy, which proposes that the Earth is the fixed centre of the universe, is actually a very powerful theory of our observations of the sky, and it was used until very recently in navigation, even though it was known to be completely false. We can use Ptolemaic astronomy to predict the motions of the planets, but we can't use it to explain them. So the deductive-nomological model is wrong to claim that prediction and explanation differ only in terms of when they're given. Good predictions can't always serve as good explanations. Now, I don't think this is really much of a problem for Hempel. We would just need to add the stipulation that a good explanation appeals only to facts that are known to be true, and as I've already noted in the previous video, Hempel does in fact make that stipulation. And after all, when Ptolemaic astronomy was believed to be true, it would quite rightly have been regarded as a good explanation for the motions of the planets. So, I'm not really sure that this is such a serious problem. A rather more serious difficulty is posed by cases which show that the deductive-nomological model is not sufficient for explanation. So we have a case that fits the deductive-nomological model, but is not an explanation. A classic example here is the flagpole. Say we have a flagpole and it produces a shadow in the sun, and we want to explain the length of the shadow. Well, that's fairly straightforward. We cite the height of the flagpole, the position of the sun in the sky, and certain laws of geometric optics, and then we deduce the length of the shadow. Okay, that's fair enough. That's a perfectly fine explanation. The trouble is that we can run this backwards, as it were. If you have the length of the shadow and the position of the sun in the sky and the laws of optics, you can deduce the height of the flagpole. So Hempel will say that you've explained the height of the flagpole by the length of its shadows. Similarly, if you take the height of the flagpole, the length of the shadow, and the laws of optics, you can deduce the position of the sun in the sky. So the flag and its shadow explain the position of the sun. Surely this is the wrong way round. It seems here that explanation is directional. It goes in a certain direction, and the deductive-nomological model just doesn't respect that. Now this objection is, I think, often seen as kind of a knockdown argument against Hempel's model, but Hempel himself was quite dismissive of it. He says that this problem is purely pragmatic. He essentially says, yes, we can explain the position of the sun in the sky by appealing to the flagpole and its shadow. It's just that this isn't a useful explanation. Remember that for Hempel, understanding is simply a matter of expectability. You understand X when you show that X was to be expected. And based on the facts about the flagpole, we can show that the position of the sun in the sky would be expected. So Hempel's thought is that the point of philosophical analysis is to kind of uncover the formal structure of explanation. And that's all. Philosophy can't tell us whether an explanation will prove to be useful. That's something that can only be determined by scientific work and by trying to apply the explanation in the context of technological development and so on. Now, very few people have found this kind of answer satisfying, mainly because it seems that philosophers actually can say something about the directionality of explanation. So notice that the sun and the height of the flagpole together cause the flagpole's shadow. However, the sun and the shadow don't cause the height of the flagpole. Similarly, the flagpole and its shadow don't cause the position of the sun. So it seems that what's missing from Hempel's model is causation. Now, as I've said, empiricists aren't happy about appealing to causation, but that seems an obvious place to look to fix Hempel's model. Another problem is explanatory irrelevance. Wesley Salmon has this nice example. Premise 1, all males who take birth control pills fail to get pregnant. John Jones is a male who takes birth control pills. John Jones fails to get pregnant. The deductive-nomological model would count this as a perfectly good explanation of the fact that John Jones fails to get pregnant. Now the trouble is this seems to attribute Jones's failing to get pregnant to his taking birth control pills, which is obviously irrelevant. The fact that he took birth control pills is not the explanation for why he failed to get pregnant. Notice that, as in the previous objection, what's missing here seems to be a concept of cause. Taking birth control pills doesn't cause John's failure to get pregnant. It's just the fact that he's male. So what should Hempel say about this? Well, maybe we could argue that premise 1 isn't a law, but it's certainly an exceptionalist regularity, and it would also support counterfactuals. Perhaps a better response is to say that any law cited in an explanation must be as general as possible. If you think about the law cited here, that all males who take birth control pills fail to get pregnant, well, clearly all we've done here is we've taken a more general law and then we've sort of artificially built something into it, right? We've artificially built into it the claim that about birth controls. The law should be all males fail to get pregnant. So in general, if we have an argument like this, premise 1, all x and y is z, premise 2, John is x and y, conclusion, John is z, the thought is we should check if we can remove either x or y from the argument. And if you can, if you can sort of cut out the y, so you just have all x is z, John is x, John is z. If that still works, then you shouldn't give this explanation. You should just give the explanation appealing to x. Hempel himself said, again, that this is just a pragmatic matter. So he was actually happy to accept that this thing about birth control is an explanation. It's just not a useful explanation. And we might say it's not useful because it doesn't appeal to the most general laws. Okay, a final objection. Consider this explanation. Most people with most bacterial infections are cured by taking penicillin. John has a bacterial infection. John takes penicillin. John is cured. So the deductive-nomological model again would say fine explanation, but suppose unbeknownst to us, John's infection is penicillin resistant. Well, then surely this isn't a good explanation. John's infection was cured by his immune system alone. The penicillin made no difference. The inductive-statistical model would say that this explanation is perfectly good because the premises are true as far as we know. But surely if an infection is resistant to penicillin, the fact that John took penicillin can't explain his recovery. So I think what we might say in response to this is just to say that actually explanation is dependent on what we know. Explanation is something we do. It so happens that this explanation is wrong, but that doesn't make it a bad explanation. And recall also that the empiricists tended to be anti-realists anyway. So any explanation that cited, electrons or mitochondria, in fact, even talking about bacteria, that's not something the anti-realists are going to believe in. They're going to be agnostic about all of that. So it seems to me that it is acceptable to give explanations that are based on false theories, as long as those theories are confirmed and verified as far as we know. So I'm not really sure this is such a problem, but that's one objection that some have made. Okay, that's all for now. Thank you for watching. Goodbye.